Hello, everyone. I have to say something before I start the session. I'm Moroccan as well, as Abdel mentioned. And you can hear that I'm losing my voice. So I shouted so much yesterday. So sorry for the not so good voice. But yeah, it was definitely worth it. Um, so aside from Morocco winning, I'm Mohammed. I work as Spotify as a backend engineer. And today we're going to talk about how we can build software, services, architecture in a safe way. You notice I'm losing my voice, but sorry for that. In a safe manner. And we probably all in this room agree that innovation at speed becomes more and more required. Users and clients no longer wants to wait for weeks or even days to get their features implemented, to get their bugs fixed, to get their user experience improved. The more you can deliver feature to your user, the more engagement you have, the more the share of your users have, the more you grow your user base, and the more good numbers mean for your business. However, moving fast is not enough. We all know a company that I will not obviously mention the name that was bragging about moving fast at some point. And they managed to deliver value and they managed to drive innovation. However, they forgot about security and they break this trust relationship between them and their customers, between them and their users. So DevOps is definitely desired. From a team, we want to move fast. We want to deliver things faster. We want to make our user happy. We want to innovate faster. However, security is also required. Security is important to make sure that the releases that we ship, the software that we ship, the services that we release are secure. And this is what DevSecOps is trying to do. It's trying to bring everyone to the table and make sure that we deliver releases that are secure. So DevSecOps try to save a seat to everyone in the table. It enables the developers to do what they do best, to add new features, fix bugs, and deliver innovation, and enable operation people to, once they have the thumbs up from the developers, they ship the software and they ship the services as fast as they can. And also have a seat for security people to make sure that the software that we release is safe and secure. So you'll probably figure it out. Today's presentation is going to be about Formula One. So anyone watching the Formula One Drive to Survive documentary? Good, awesome, a lot of people. So for the people that doesn't know about it, this is a Netflix kind of TV show, reality, about behind the scenes of the Formula One. And it tells the story of the drama that is happening in the paddock, all the things that happen during the races. And it's kind of a good documentary, the Netflix way, right? And I started watching it during COVID. We had a lot of time and yeah, we had nothing to do and we were like in a lockdown. And while watching one of the episodes, this actually happened. Driver from the Haas team, Roma, I think it's a French driver, it was driving super fast with 300 kilometers per hour. Did a bad maneuver, and the car hit instantly the barrier, turned into a fireball. Now, even the people that works in the Formula One, the FIA, which is the organization that oversees the Formula One races, were worried about the severity of this accident and how bad it was. And by our measures, the normal people, this is actually a death sentence. Imagine a car accident happening this fast with this damage. Probably hope that if the driver is alive with a lot of damage, with a lot of injuries, then that's a win. But guess what? Roman managed to get out of the car on his own feet. Crazy, right? And that got me thinking that the designer, the architects, and the FIA of the Formula One, they might be doing a lot of things right to keep the safety of the drivers while looking for speed, while innovating for speed, actually. And that got me thinking what would happen if we design our architecture, our systems, our services with the same level of devotion that the Formula One engineers designed their cars. Now, throughout the episodes and throughout the documentary, they kept mentioning safety and not necessarily mention the security. Now, I'm not a native English speaker, so I use them interchangeably, right? However, when I opened the dictionary, I found that the security means the state of being free from danger or threat. Now, from a software engineering perspective, this is not what we're trying to achieve, right? We know that from the moment we put a service to the internet, there are thousands of things that will go wrong. There are thousands of malicious users that will try to break your system. There are millions of bots that will basically try to flood your system and break your application and brings it to your needs. However, safety, on the other hand, means the condition of being protected from risk, danger, or injury. And this is what we are trying to do as well in software engineering. We know that the system is not safe when we put it in the internet. We know that the environment is not safe. We know that there are a lot of things that can go wrong. However, we try to do as much as we can to keep it protected. And even if the damage happens, we try to minimize the damage and keep it small. And that got me thinking, what happens if we start design architecture with safety in mind? Good architecture should let the developers, the IT people, move as fast as they can while keeping the safety on the back of their mind. Sorry, I need to have a drink. So I started a journey to look into the safety measures and the rules and the regulation that FIA added throughout the years in order to ensure the safety of the drivers during the Formula One. And I picked 10 rules. 5 of them are pre-crash measures, the things that the drivers and the teams need to ensure before the drivers get into the race. And the other 5 are post-crash measures, the things that they do or they ensure after the crash or when the crash happens. And from a data point of view, it really works. There are 2 diagrams that show that the one is the number of deaths compared to when the FIA added more regulations. And you can see that the more regulations we have, the smaller or the fewer deaths we have in the Formula One. And the latest one was in 2014. So Formula One is becoming slowly, even if it's one of the most dangerous sport or motorsport in the world, it's becoming slowly safer and safer for the drivers. And the second one shows the number of days between fatal incidents. And if you compare to the previous one, you see as we add more regulations, as we add more rules, the Formula One became a little bit safer. So let's dive into the first 5 rules, just like first pre-crash measures. First one is the drivers actually, or in the car, they have a seat belt. However, the seat belt is different than the one we have in the normal cars. It has a 6-point harness, which when the driver gets into the car, it needs help. He needs help. They need help to get into the car, and they need help to fasten their seat belts because like a 6-point harness. However, and this is really important, the seat belts can be released with a click from the driver. And from a software engineering perspective, this is actually similar to the push to deploy or push to release, right? This is what we're trying to do, like automate our process to have end-to-end automation to release our software as fast as we can. And automation offers a lot of benefits. It enables your IT department to focus on innovation by removing the manual work. It reduces the amount of risks and issues and errors introduced by the manual work by automating all the stuff. And it also introduced transparency in your whole workflow. So everyone can contribute to that workflow, from developers, the security, and also the operations. The second thing Second measure is actually they have a stringent dynamic, static, and load test to ensure the safety of the drivers. And in simple words, that means they test the car and all the components in different environments and in different conditions. They test the car in a wet day, in a rainy day, in a very cold day, a very windy day, in a very hot day, a very humid day, and gather data about how the cars perform. What are the sensors? What are the metrics? If there are any issues that the driver or the car must have during a race day. And this is similar from an engineering point of view to have a trusted, repeatable, and adversarial CI/CD pipeline where we ensure that we make sure that the software, before it gets released, it goes through the same environment it will go through when it gets to production. And adversarial is really important here because we ensure that everyone's voice is heard. Developers that want to move fast, operations that want to automate all the things, and also security to add checks and add security checks to make sure that once the software is released, it is released in a secure and safe manner. Another thing we can do to ensure that our release, our service, once it hits production, it is tested on the same environment, in the same production environment, is actually canary deployment. And in canary deployment, we deploy two versions, the old service on the old application and the new one in a subset of the service, on a subset of servers. And we reroute a portion of the traffic that you can decide on to the new service. So we can test how the new application performs in the same production environment, in the same production traffic. And we can have automatic thresholds and automatic measures that automatically roll it forward or roll it back in case of issues, in case of errors. So this is a way to ensure that the new code doesn't have any bugs and regressions, especially from a security point of view, to make sure that your software is tested in the same production environment that it will go into, run into. Yeah, I like my thoughts inserted. The third thing is the cockpit is surrounded by the more formal crash protection structures. And that means they build the car around this structure, which its sole purpose, it's actually to save the driver's life. And from a software engineering perspective, this is similar to designing for failure, right? We design the car for the crash. We know that there will happen a crash. There will be a crash for sure. So we design this structure and we repeatedly test it and crash it to ensure that even if a crash happened, like the driver's life is still safe. And from a software engineering perspective, and we as developers, we should no longer design our applications with business features in mind only. We should design our application to be more fault tolerant in case of network issues, database issues, a lot of things that can go wrong, make our application more resilient and fault tolerant. A couple of things we can have here, like mutual TLS, which is an extension of TLS, but we have it in both ways. This is really important in distributed systems where both the client and the service needs to be mutually authenticated and make trustworthy before exchanging the communication. So even if an attacker managed to get inside your cluster, we have the traffic encrypted and cannot sneak what is happening and circulating inside your cluster. We can also design our architecture in a micro-segmented way. And that means we put the data and the services that owns the data, which are the most critical systems, as far away from the internet-facing systems as we can. So even if an attacker managed to get inside one of the internet-facing systems, our application will deform itself, and the attacker will still need to do another layer, another effort to get inside the services and the critical services that actually own the data. So it is similar to have a crash deformable structure that deforms itself in case of issues. And the other thing they have is before they race, the driver must demonstrate that they can get out within the car under 5 seconds. And they do that before every race, in every day, whenever they need to get inside the car. Imagine if a crash happened, I need you to get out of the car as fast as we can. So let's test that before you get into the car. If you cannot get out from the car under 5 seconds, you cannot race for the day. And from a software engineer perspective, this is similar to chaos engineer, right? Like, this is not only designing for the worst case, but it is testing the worst case. And we all know about our systems that in case of failure, we know that some issues and some attitude our services will have. But what scares me the most are the things that we don't know about our systems. So chaos engineering is kind of a practice where we deliberately make failure to understand the reaction of our system and to help to make it more resilient. And you can start small. You can start by designing hypotheses about your system and design the smallest possible experiment. You can start, for example, by starting to introduce delays in the response time of your application, and then run the experiment, and then roll it back in case it's affecting users. Otherwise, take notes of how your system, how successfully your system reacted and how bad your system reacted, and then take notes of those failures, fix them, and then you can grow gradually, and that help you to gain confidence over the resiliency of your application and your architecture. And the final thing we have in pre-crash measures is constant monitoring and replacement of the tires. Now, look at this. For the people that watch Formula Ones, they know that Red Bull is the fastest team in the paddock that changed the tires. And the world record is, for them, is 1 second and 82 milliseconds. And look how happy they are, how proud they are, not for patching the tires, not for hot fixing them, but actually for changing the tires, right? So compare this to the way we treat our service, traditional service more specifically, where we are proud of keeping them up and running for years or months, right? So this is to say that there are other measures and other metrics that we can introduce. And we all know the pigs versus cattle analogy, where we want to create our servers and our resources as disposable and not have this personal relationship where we give our servers names, our VMs names, and if there's in case of issue, we try to fix the issue and try to patch them and have this personal relationship, but treat our resources more as disposable, where we spin them up at will and remove them at will. Now, if we accept this analogy, how about pushing it a bit further to cattle versus chickens analogy? We know that the amount of time to reach adulthood for the chicken is around 6 months compared to cattle, which is 24 months. And the amount of resources you invest is much heavier and much, you need to invest more resources in order to the chicken reach, cattle to reach adulthood compared to chickens. This is to say that there are other metrics that we probably need to be worried about or care about, like the reverse uptime. And to understand reverse uptime, let's take an example. Imagine an attacker managed to get inside your cluster or inside one of your node, and then that is by itself bad enough. But imagine that he managed to hide himself and use that node as a base to attack other nodes in your cluster. Now imagine that this node is removed and replaced by a fresh node about 1 day or 2 days, whatever, 1 week. So we temporarily removed the damage and removed the risk by simply creating a new node and removing the new one. And from a security point of view, we can't backdoor a system that is constantly getting changed and revised and revamped. Right? So this is a great way from a security point of view. And the smaller the reverse uptime is, the more secure you are. Now combine this with the base image freshness, which is the base image is the golden image that you use to build up or use to run all your services and applications. Now, if you have a important vulnerability to fix, like a zero-day kernel, a zero-day vulnerability that you need to fix, you know that once you patch your golden image, the maximum amount of time that you would need to have all your cluster updated with the base image is actually the reverse uptime. Now, combining those both ensure a good security for your cluster. Now we're talking about the 5 pre-crash measures. Let's dive into what we call the post-crash measures. When the car crashed, what are we going to do? The first thing we have is the driver can be extricated from the car by lifting out the entire seat. So if the crash happened and the driver passed out, if we can't get the driver out from the car, we don't try to do whatever crazy things to get the drivers out, but we simply lift out the entire seat and get the driver out from the crash scene. I'll compare this to a normal car accident where we lose precious time trying to open the door and get the drivers out. And from a software engineering perspective, this is similar to designing your application in a modular way, enable you to pull the plug or react as fast as possible to your components, right? Like the Formula One people managed to design the car in a modular way, enabling them to pull out the entire seat with the driver out from the crash scene. And this is similar if you have a bad day, how fast you can react to a certificate that is getting exposed to the internet, or a SSH key, or your secret. So the more loosely coupled your components are, the more faster you can react in case of issues, in case of incidents. And there are great benefits from having a loosely coupled system. First, you have fewer dependencies for your system. You have failure isolation. If one component failed, you are sure that the other systems will still be healthier, and you can have other patterns that we're going to talk about to ensure that if one components fail, other components can still be up and running. And I just noticed a typo here. And you have evolvable architecture. You can grow your architecture and add more components without being relying on one component. The other thing we have is a HANS, and HANS stand for head and neck system. And the job of this system is actually to absorb and redistribute the forces that would otherwise hit the driver's skull and neck muscles. And the HANS is this little piece. And it has a very important job. When the crash happens, because the driver are driving super fast, the forces that generated by the crash are crazy, right? Like imagine driving super fast and the crash happen, the force that we'll get are, God knows how much. So the job of the HANS system is basically to distribute the forces generated by the crash through the driver's body that would otherwise hit his head, neck, and muscle systems. And from a software engineering perspective, this is similar to having an elastic architecture where we have tools in place that help us to reload the traffic and balance the traffic in case of issues. Starting with having a load balancer. If you're having a bad day, if you're having a very good day, and having traffic is a good day, right? If you're having a very good day and you're having a lot of traffic, have a load balancer that can redistribute the traffic across all your nodes is good to ensure the health and the resiliency of your system. If you're having a very, very, very good day and the nodes that you have can't keep up with the load, having auto-scaling that can spin up other nodes to handle the traffic can save you from incidents. If one of the services is acting bad and taking more time to respond, you can have request time threshold to save up the threads and the resources and not keep the threads hanging waiting for the response. So having request time threshold is really good from a resiliency point of view. In a lot of cases, having a degraded performance, that's depending on your business and your software, but having a degraded performance is really good than not responding at all. And also implementing some anti-overload patterns that are circuit breaker and exponential backoff can help if you are having a lot of load or your system is starting to act weird. So you have 5 minutes, right? The other thing we have is the driver's suits are fire resistant. And this is how our friend Roma in the beginning managed to get out. So the suit that the driver wears is actually capable of keeping the driver's body under 41 degrees Celsius, even if in the extreme heat outside. So even if it was like Roma was in a fireball, but the suit was capable of keeping his body temperature under 41 degrees Celsius. And it's really important to contain the drivers and keep his the driver's body under an acceptable temperature. And this is similar to containing the damage and containing the risks of breach, right? And there are a couple of patterns that we can implement to alleviate that, starting with making sure that we're on our application and software with the least privilege principle, making sure that the services that we're on and the nodes that we're on are run with the least set of access rights and resources, making sure that our application does not perform bad or act weird. If an application doesn't need write access, fine, don't give it write access, give it only read access. So that would help to ensure the security of your application. Also, defense in depth and design your architecture with layers. So even if an attacker managed to sneak in and breach one layer, he will face other layers to breach and will have more work to do. And following the zero trust principle and forcing authentication between all parties and having no implicit trust. Anyone, each service, each user that wants to make a call or make a request to your services or your system needs to be authenticated. Another thing we can have is the hardware security modules, which so probably an example would help to explain this. Imagine that you have an application that manages user's password, right? And that manages user password, and you have a very strong algorithm that encrypts those passwords. So each time a user use a password, you put it into your encrypted or your encryption algorithm, and then you decide if the password matches or not. Now imagine an attacker managed to get in and get the data out of your cluster. Now he will have a lot of time to try to break your encryption algorithm, and you won't know about it until it appears the next day in the news and in the black market. Now compare this with having a hardware security module where each time you would need to encrypt a key or encrypt a password, you will require a key from a security module, from a hardware security module. Now, even if an attacker managed to get access, he would also need the key. So he cannot get the data out of your cluster. He would still need to be in the cluster because he would need that key each and every time to decrypt the passwords. So you are keeping him inside, and you're containing the damage. Hopefully, you would notice his presence and take any necessary action to kick him out. The fourth or third thing is fire suppression system that can be activated by the driver externally or by the race marshal. And the fire suppression system is basically a system that control and minimize the fire damage. And notice how it is distributed the access depending on the use case. So if a crash happened and there is a fire, if the driver is still awake, then he can trigger the suppression system. If there a crash happened and the driver passed away and the rescue team is there, they can trigger it from a button outside the car. And if the driver passed away, the crash scene, there is a big fire, the race marshal can activate the system remotely. So this is really important of giving access to the people that need it, but not being overly optimistic. And there are a lot of methodologies and tools that you can implement to make sure that you give access to the people that it needs without giving access to everyone or locking yourself out of your door. one thing. Yeah, almost there. Data recorder that keeps speed and decision forces, so doctors know the severity of the impact. The Formula One people are crazy about data. For each run, they collect around 1 terabyte of data. So they have data about everything, acceleration, deceleration. So when a crash happened, they know already how severe the crash was, and they share those information with the doctors. So when they arrive to the crash scene, they know already how bad the crash was. And needless to say, that no system should go to production without monitoring tools in place. Since I'm running out of time, um, this is how the Formula One people or the drivers looks in their car. It's really not comfortable, but from an aerodynamic perspective, is really optimal. So this is a trade-off that you need to balance between the business and the security. And um, this number scares me from data breach report from IBM Security that the cost of cyber attacks is more than 4 millions. However, to detect a breach, we need almost 280 days. It's almost 10 months. So it's really long time to understand a data breach, and that is something happened in your cluster. So I hope throughout this presentation, we have some insights on how to move fast, deliver value faster, while keeping our architecture and system safe. Thank you.